Look inside any modern high-rise, and you will find a massive collection of isolated mechanical nodes. Thousands of electrical conduits, ventilation fans, and localized chillers operate simultaneously, yet completely blind to one another. To manage this density, engineers deploy a Building Management System, or BMS. A BMS is an active, closed-loop network designed to monitor conditions, process logic, and physically execute mechanical adjustments in real time. The core engineering challenge of building this system is hardware diversity. The HVAC chillers on the roof, the security doors in the lobby, and lighting grids on the floors are manufactured by dozens of different vendors. Out of the box, they do not speak the same digital language. When these subsystems cannot communicate, they operate inefficiently. A localized heater might trigger in a room where the central air conditioning is already working to lower the temperature, wasting massive amounts of energy. True building automation depends on a standardized communication topography, engineered from the bottom up to force disparate systems into a single, cohesive loop. This diagram illustrates the industry solution to that hardware chaos, a universal three-tiered hierarchical architecture. At the foundation is Tier 1, the field level. This consists of the physical sensors, valves, and fans deployed directly in the physical environment. Sitting directly above them is Tier 2, populated by Direct Digital Controllers, or DDCs. These act as localized processing hubs, bridging the gap between physical machinery and digital networks. At the apex is Tier 3, the system or management level. This is where the primary servers and operator workstations sit, overseeing the entire topography. Adhering to this specific, rigid hierarchy is the only way engineers prevent integration failure when managing hundreds of thousands of active data points. Zooming in on Tier 1, the sensors act as the sensory organs of the building. They continuously gather raw analog or digital data, measuring fluctuations in temperature, humidity, and air pressure. Working alongside them are the actuators. If sensors are the senses, actuators are the muscles. They receive incoming data commands and execute mechanical changes, like physically rotating a damper or opening a chilled water valve. Connecting these two components require Tier 2, the Direct Digital Controller. This hardware acts as a local brain for a specific physical zone. DDCs run localized logic loops. They constantly ingest the raw data wave from the sensors, run it through pre-programmed algorithms, and fire immediate commands back down to the actuators to maintain a precise set point. This localized processing provides a critical safety buffer. Because the DDC runs its own logic, it operates independently. If the main Tier 3 server crashes or the network goes offline, the DDC keeps its specific HVAC zone running safely. Tiers 1 and 2 effectively form the autonomous reflex arcs of the building. They secure basic operational safety without ever needing to ask the master server for permission. Moving up to Tier 3, the centralized BMS server takes on the role of the master brain. Its primary function is to aggregate the thousands of disparate data streams flowing upward from the localized DDCs. This centralized data enables global energy analytics, facility-wide scheduling, and the primary user interface for human operators. But connecting Tier 2 to Tier 3 presents a major technical hurdle, getting the localized DDCs from varying manufacturers to successfully transmit data to the central server. The solution relies on communication protocols. A communication protocol is a standardized set of rules for formatting and processing data. To unify a building, engineers rely on strict industry standards: BACnet for HVAC equipment, Modbus for electrical meters, and OPC for complex industrial processes. These protocols function as real-time translators. They strip away the proprietary hardware signals from different manufacturers and convert them into standardized network packets the central server can rapidly ingest and analyze. Without rigorous protocol standardization at the network layer, the top-tier management server remains entirely isolated from the physical infrastructure below it. Deploying this three-tiered architecture requires a sequential engineering workflow. On a greenfield project, meaning a brand new construction, engineers start with a blank slate. Step 1 is the site survey. Engineers must define exact functional requirements, set strict energy consumption targets, and comprehensively map out the mechanical, electrical, and plumbing designs. Step 2 is architecture design. Here, engineers select the specific field sensors and DDCs and map out the exact communication network topology required to link them. During this phase, they must architect a rigid database structure. Every single piece of hardware requires a unique digital address, so the server knows exactly where incoming data is originating. The third step is installation and commissioning. After the physical deployment of wires and controllers, technicians execute rigorous fault testing, deliberately triggering system failures to verify the DDCs respond correctly. Designing a new BMS relies entirely on this deterministic workflow. Skipping the site survey or rushing the database design guarantees mapping errors and widespread integration failure. Engineering becomes significantly more complex in a brownfield scenario. This involves designing and integrating a brand new subsystem into an older, already operational BMS. Before drafting a single new schematic, engineers must meticulously analyze the legacy protocols and out-of-date database structures running the current building. The operational risk here is absolutely massive. Patching modern hardware directly into an old network can introduce data collisions, potentially destabilizing the entire building's current mechanical operations. The primary constraint is backward compatibility. The newly designed subsystem must enhance the facility's capabilities without breaking or overriding the existing DDC logic loops already in place. This step requires intense, isolated integration testing. Technicians verify that the legacy system and the new hardware interact perfectly in a sandbox environment before pushing the update live. Brownfield engineering rarely focuses on installing physical parts. It is an exercise in safely navigating network bottlenecks and resolving database conflicts. To manage the friction of protocol translation and complex database integration, facility engineers utilize enterprise-grade management platforms, such as Siemens Desigo CC. A platform like Desigo CC acts as an overarching universal translator. It natively supports multiple open communication standards, including BACnet, OPC, and LANWorks, simultaneously. It ingests raw network packets from entirely different vendor hardware and abstracts that underlying complexity, presenting the operator with a single, unified digital interface. By abstracting the communication layer, the software frees up processing power and human capital. Operators transition away from troubleshooting basic data connections and focus directly on predictive maintenance and automated energy optimization. High-level enterprise software absorbs the technical burden of protocol translation, allowing facility engineers to actually optimize the performance of the building. We can trace this entire automated sequence from the bottom up. A Tier 1 temperature sensor detects a sudden heat spike in a conference room. It sends an analog signal to the Tier 2 DDC, which digitizes the reading, wraps it into a standardized BACnet packet, and pushes it up to the Tier 3 server. The Desigo CC server instantly processes this data against its facility-wide parameters. Within milliseconds, it sends a command down a completely different network branch to dynamically dim the local lights and increase the output of the roof chiller. This layered engineering, bound by strict communication protocols, enables a building to adjust its physical state in real time, responding to environment shifts as they occur.